Hello. Here we are at the beginning of 1.6. Bases, 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 and coordinates. This isn't bases like in baseball. This is the plural of basis. Basis. Oh my gosh, I'm out of practice. I haven't said these words out loud in a while. I've been on sabbatical at home typing and I forgot how to pronounce everything. So multiple bases are not the same thing as multiple bases, like in baseball. Okay, bases and coordinates. Here's a definition of a basis. You've got a subspace of Rn. Last time we saw that basically means that U must be the span of some vectors from the theorems at the end of 1.5. There's some linearly independent list of vectors that spans U. And this also applies to U could be equal to Rn. So we could also talk about a basis for Rn. So anyways, a basis for U is a list of vectors with this like fancy script B. And I don't know if you have like fancy cursive writing. I kind of just write a capital B with a curly back like that. And that's B. So it's a list of C vectors that is one, linearly independent, and two, oh, this is a mistake. This really needs to be the span of B equals U. One moment. All right, we have fixed the typo. Yeah, it's a basis for U if it spans U. Like everything in U can be written as a linear combination of these basis vectors. By the way, we're using the fancy script B because this means that like indicates we're talking about a basis, and just a regular capital B is usually going to be a matrix later on. And this helps keep them apart, tell them apart. Okay, let's look at example 1 here. Is this list of two vectors a basis of R3? For all these examples, I recommend pausing it before I show you the answer, thinking about it, trying it on your own. It's okay if you just want to make a guess, just to think about it a little bit without just listening to me all the time. So, okay, so I'll tell you the answer in 3, 2, 1. And it is linearly independent. There's a few ways to see that. You could see that neither of these is a multiple of the other. There's other ways to think about it too. You could actually go ahead and solve the homogeneous equation using just the definition of linear independence, and you'll get the only solution is the trivial solution. Okay, part 2 of the definition. Is the span of B equal to U? No. So it does meet the first part. It does not meet the second part. If you think about it, in 3 dimensions, the span of these two vectors is going to be a plane that includes these 2 points and the origin. And that's not going to be a 3-dimensional space-filling thing. You could also think about how there's only 2 pivot positions, other ways to see it, but the span is not equal to all of R3. Okay, that's not a basis. Let's look at example 2. Is the same set of 2 vectors as example 1. Is it a basis of the span of itself? We know the span of itself is a subspace of R3. So I will tell you the answer in 3, 2, 1. Yes, it is. So it's still linearly independent because it is still the same list of vectors as before. But now the question is the span of this not equal to R3, but is it equal to itself, right? Because when we say a basis for U, the span of B needs to be U. And that's our subspace. So is the span of B equal to the span of B? Sure is. So yeah, it meets both conditions. Let's look at example 3. This is like a script E. This is like super old-timey cursive script that nobody knows how to read anymore. But this is a special list of vectors. This is called the standard basis vectors. We write them as E1, E2, and E3 here. And this matrix that has them as its columns is called the identity matrix. And it's a special matrix. We can write subscript 3 just to indicate that it's 3 by 3. Okay, so yeah, let's pause the video because I will tell you the answer in 3, 2, 1. Oh yeah, we actually already kind of answered these questions in the warm-up. So yeah, this is linearly independent because it's got a pivot in every one of these columns here. And it definitely spans R3. Cool. So those are bases. Let's look at a few more to get an idea of this. Here's example 4. We've got this list of 3 vectors. Is that a basis of R2? In other words, is B linearly independent? And is the span of B equal to R2? I'll tell you the answer in 3, 2, 1. No. It does span R2. If you were to row reduce the corresponding matrix, you'd get pivot positions in every row. But it's not linearly independent because you have a non-pivot column. You're guaranteed to have a non-pivot column because you can only have a maximum of 1 pivot per row. So even without thinking about what the numbers are, you know one of these 3 is going to be a non-pivot column. Okay, let's look at one more. Example 5 gives the same list of vectors as we had in example 4. And now the question is it a basis of the span of itself? So pause it real quick and I'll tell you the answer in 3, 2, 1. So it's still not linearly independent. It is dependent. The span of it is itself, but what this tells you is that if you have a linearly dependent set, it can't be a basis of anything. But a linearly independent set, like in example 2, it can be the basis of something. It's just maybe not going to be the basis of all of R3. All right, quick introduction to bases there. And in the next video, we'll look at coordinates.